class, welcome back to thermodynamics. In this lecture, we're going to keep pushing onward and practicing with entropy balances using the second law of thermodynamics. So today, what we're going to do is we're going to go through one problem together, and then I'd like you to pause the video and try the second problem completely on your own. So let's begin with 6.70, number 70 from chapter 6 in your textbook. And that says a cylindrical copper rod of base area A and length L is insulated on its lateral surface. One end of the rod is in contact with a wall at temperature TH. The other end is in contact with a wall at a lower temperature TC. At steady state, the rate at which energy is conducted into the rod from the hot wall is Q dot H is equal to kappa A times TH minus TC over L. So this equation should look very familiar to you. This is the conduction equation for heat transfer. And kappa is the thermal conductivity of the copper rod. And let's just draw a little sketch of our copper rod to begin with. So we're going to have a rod of length L. And it's going to be well insulated on its lateral surface, meaning that we're getting heat transfer across it in this direction. And so we have some area A, we have TH, we have TC, and the length is going to be L. So for the rod as the system, obtain an expression for the time rate of entropy production in terms of A, L, TH, TC, and kappa. Let's start there. Now, we need to derive entropy production, the rate of entropy production. So entropy production is sigma, and the dot above it, remember, is a rate. So that'll be kilojoules per kilogram Kelvin per time per second. So we have a rate of transfer there. And everything that we have to use is A, L, TH, TC, and kappa. So let us begin with an entropy balance. So we know that ds over time is going to equal the integral of del Q over T minus del Q. So it's going to be the integral of del Q over T. And so once we evaluate that, we can write it out as Q dot H over TH for the higher temperature end minus Q dot C over TC. And remember, then there's also going to be the entropy production. All right, so that's coming from this relation we've been using. Where'd it go? We look back. Let's try last lecture. I just had this all set up. Bear with me. Anyway, oh, last lecture. Oh my. There we go. So that'll be from this piece right here. That's where that comes from, this entropy balance. Okay. So now, well, ds over dt is going to be 0. This is steady state for entropy production as well. So this is the rate of entropy with time. So that tells us that sigma dot is equal to Q dot C over TC minus Q dot H over TH. So steady state tells us that Q dot C is equal to Q dot H. Same rate of heat transfer. And so we can rewrite this then, since Q dot C and Q dot H are equivalent, we could say that sigma dot is equal to Q dot H times 1 over TC minus 1 over TH. Okay, so that's just coming from up here. I just pulled out the QH because QC and Q dot H are equivalent. And then for Q dot H, I'm going to plug in our conduction equation. So we have kappa A times TH minus TC over L times 1 over TC minus 1 over TH. And I'm going to open up another sheet for us to keep going. And really, we just have algebra left at this point. So for this, we're going to just keep going with our algebra. So sigma dot is going to be kappa A TH minus TC over L times 1 over TC minus 1 over TH. And I am just going to multiply this whole thing by 1, doing TC over TH, TC times TH over TC times TH to see if I can get all this mess out of the denominator. And so this is going to be kappa A over TCTH times TCTH. So I'm just moving this. Okay, and then if I distribute this through, we have TH over TC minus TH over TH minus TC over TC plus TC over TH. Okay, so I just have the TH minus TC inside here as well included. And then next, what we're going to do is let us try to get rid of the denominators in here. So this is going to be kappa A TCTH, and we're going to multiply through by TCTH. So we're going to end up with TH squared minus TC TH. So this is where we have TC TH times TH over TC. So the TC's cancel and we end up with TH squared. So I'm just going to keep going through in that regard. Minus TC TH plus TC squared. And so this is going to give us kappa times area times TH minus TC squared over TC TH. Okay, and so that is going to be our sigma dot, our entropy production, entirely in terms of kappa, area, TH, and TC. And so for the next part, we need if TH is 327 degrees Celsius, TC is 77 degrees Celsius, kappa is 0.4 kilowatts per meter per Kelvin, area is 0.1 meters squared, then plot the heat transfer rate in kilowatts and the time rate of entropy production in kilowatts per Kelvin, each versus L ranging from 0.01 to 1 meter. Discuss. So let us just go through this last part. So for this last part, TH is 327 degrees Celsius, TC is 77 degrees Celsius, K, kappa, the conductivity, the rate of conductivity is, for copper, is 0.4 kilowatts per meter Kelvin. And the cross-sectional area of our copper cylinder, copper rod, is 0.1 meters squared. So what we're trying to plot is, we have two plots. We're going to have Q dot, so the rate of conduction, against L, and we're also going to want the rate of entropy production, sigma dot, against L. So it's like, how does this vary with an increasing length from 0.01 to 1 meters for L for our rod? So if we were going to go through and do this, we end up with, well, the rate of heat transfer is going to drop off the longer the rod gets, and the same goes for the rate of entropy production. So that is it for that. And so just remember that with conduction, this is energy transfer, heat transferred via contact along a temperature gradient. Okay, so you have to have two different temperatures here. Now, on your own, I'd like you to try this problem. A closed rigid tank contains 8 kilograms of molecular hydrogen, where R, for hydrogen is 4.116 kilojoules per kilogram per Kelvin, initially at 400 Kelvin. The tank is in contact with a thermal reservoir at 700 Kelvin, and heat transfer occurs at the boundary where the temperature is also 700 Kelvin. A stirring rod transfers 15 megajoules of energy to the hydrogen. The final temperature is 700 Kelvin. The hydrogen can be modeled as an ideal gas with K equal to 1.396. Kinetic and potential energy effects are negligible. So first, you're going to sketch the process on a TS diagram. Second, you're going to determine the specific heat capacity for the process. Third, you're going to calculate the amount of entropy transferred into the hydrogen. And finally, you're going to find the amount of entropy produced based on this image here, where you have work is minus 15 megajoules. So think about the direction of that work. Okay, so it's going into spinning the paddle wheel. Also, we have T reservoir is 700 Kelvin, and T2 is 700 Kelvin, and hydrogen is initially T1 at 400 Kelvin, 1 bar. So pause the video, give this a try, and then when you're ready to see the solution, hit play to resume. So I'm going to keep going here, and let us just start by sketching this on a TS diagram. So it's this temperature, entropy diagram. And I'm going to do temperature in Kelvin. And entropy is kilojoules per kilogram Kelvin. Okay, and so we're dealing with an ideal gas. So I'm going to draw the vapor dome super tiny and in the lower left corner, because since we're far off in ideal gas land, and we're going to start at some initial entropy, and we're going to have some final entropy. And our initial temperature is 400, and our final is 700. So entropy is going to increase with increasing temperature, and so state 1 is down here, state 2 is up here. Okay, so that's it for part A. That is the process sketched on the TS diagram. So next, we're going to determine the specific heat capacity for the process. So B, we're given K, and remember that K is equal to Cp over Cv. Also, that Cp is equal to Cv plus R. So K is equal to Cv plus R divided by Cv, which tells us that Cv is equal to R over K minus 1. So we have all the information we need there. We just need to plug in R and we need to plug in K. So I'm going to open up a new sheet to do that. So Cv is going to equal 4.116 kilojoules per kilogram Kelvin divided by 0.396, which is going to give us 10.39 kilojoules per kilogram Kelvin. So now the next piece, part C, was to calculate the amount of entropy transferred into the hydrogen. So let us do an energy balance. So Q minus W can be found using mCv delta T. And we're given the work, minus 15 megajoules. So Q is going to be mCv T2 minus T1 plus W. Okay, and so this is going to be, M is 8 kilograms, we were given that. CV we found above, so that's 10.39 kilojoules per kilogram Kelvin. And then we have T2 minus T1, so T2 was 700 minus T1, which was 400. And then we have to add work, which was minus 15 megajoules, which is 15,000 kilojoules. So this is going to give us Q is equal to 9,940 kilojoules, or 9.94 megajoules. Okay, so that is going to give us Q, but we need to find the amount of entropy transferred into the hydrogen. So delta S is going to equal Q well, the amount transferred into the hydrogen, looking back at our figure here, is going to be Q over TB, where TB is our temperature of the reservoir. So then Q over TB gives us the entropy transferred into the hydrogen, which is going to be 9.94 megajoules over 700 Kelvin, which is going to be 14.2 kilojoules per Kelvin. Okay, so that is it for part C. Now let's look at our last part, and that is to find the amount of entropy produced. So we need to find that sigma, that entropy production. So let's add another new page. So delta S is going to equal Q over TB plus sigma. So sigma is going to be delta S minus Q over TB. All right. So now we have to figure out what delta S is. So delta S is going to be m, the mass, times CV times the natural log of T2 over T1 plus R times the natural log of V2 over V1. And we derived this last lecture. And so here's the thing. We are dealing with a closed, rigid tank. So delta V is 0. So that means this is 0. And now we have T2, we have T1, we have CV, which we figured out in part B. We have our mass, and we have Q over TB. Okay, so now we can get our entropy production. So sigma is going to be M, which was 8 kilograms, times CV, which was 10.39 kilojoules per kilogram, Kelvin, times the natural log. T2 was 700 Kelvin, T1 is 400 Kelvin, so 7 over 4. And then we want to subtract off Q over TB, which was 14.2 kilojoules per kilogram. We found that in part C. Kilojoules per Kelvin, sorry. So entropy production is going to equal 46.5 minus 14.2 kilojoules per Kelvin. And that is going to be 32.3 kilojoules per Kelvin. All right, well, that's it for today. Hopefully you were able to work through that successfully on your own. And just remember, with thermodynamics, keep practicing, keep working through the problems in your book. The more you practice, the quicker you get at noticing these patterns and being able to solve these problems and being able to apply the first and second laws of thermodynamics. And I will see you next time. Take care.